In this video, we're going to derive a parallel algorithm for the sparse matrix vector multiplication. And we do this by first distributing the data and then representing them in a local data structure. This assigns non-zeros to processors and then stores the non-zeros in a local data structure. And this is much better than doing the other way around, because if we have a global data structure and then distribute the non-zeros of the matrix, then we would complicate all simple operations, like inserting a non-zero in the data structure would require collaboration between processors. And now this is a local operation. So we can define a data distribution as a mapping between non-zeros and processors. So a non-zero Aij is assigned to a processor with a number that we call phi of ij. So it's dependent on the row and the column index of the number. And we don't assign zeros to processors, but just to be able to talk about them with the mapping, we just assign a dummy variable -1 to phi ij. Here we see a distribution of both the matrix and the vectors, and this is to the left a global picture. We have a blue and a red processor. The red processor is processor 0, the blue processor is processor 1. And you see here that a number of non-zeros are assigned to the red processor. And to the right, you see the local view of this processor, containing only the non-zeros and their rows. So the rows that contain a non-zero or the columns that contain a non-zero. The question now, after the distribution, is where do we compute the multiplication of Aij and Vj, of the non-zero of the matrix and the vector components. Since there are many more non-zeros usually than vector components, it makes sense not to move the non-zeros, but to move the vector elements. So we bring the vector element Vj, we transfer it to the processor that owns Aij, and then we perform the multiplication there. And we can also, if we have more non-zeros in the same row of the matrix, we can then perform all those multiplications locally. And then we get a result, which is a partial sum, and it's a contribution to ui for processor I, but it's a contribution by processor S. And this contribution we call uis. So we do not communicate elements of the matrix. We only communicate components Vj and contributions to components ui. So then the question is, how do we distribute the vectors? This could be in any way. It becomes an assignment of ui to, and here we call the mapping phi u of I. And we can do that for the input vector, for the output vector. And sometimes you want to repeatedly multiply a matrix by a vector, and then it is convenient that the output of A times V, which is U, is in the same distribution as the input. And that way we can repeatedly multiply without having to redistribute the data. On the other hand, there are algorithms that multiply first by A, then by A transposed, and then it is convenient, and you have the freedom to have an input distribution for U, output distribution, and they need not be the same, because the output of A times V becomes the input for the transposed algorithm. And the transposed algorithm basically does all the operations in the reverse order. So this is a nice chaining of the operations. So deriving a parallel algorithm, what we're doing basically is we have a data distribution the algorithm follows from this distribution. And what we're really computing locally is UIS, which is the sum of all the Aij, Vj of the elements that are mine in row I. So to facilitate the derivation, we need some notation. And the first important notation is IS, which is the index set of processor S, and it contains all the rows that locally are non-empty. So in the case of the red processor, you see row 4 is empty, but rows 0, 1, 2, and 3 contain a red non-zero. And because of that, the index set is 0, 1, 2, 3. And similarly, for the blue processor, we have the row index set 0, 2, 3, 4. And we can do something similar for the columns. So JS is the index set of columns that are locally non-empty. Now my question to you is, what are J0 and J1? Okay, you probably found this was an easy one because you can find the answer on the picture. J0 is the index set, the column index set of the red processor, and that's 0, 1, 2. And the blue processor, so that's J1, has indices 2, 3, and 4, because columns 2, 3, and 4 are non-empty. Now we're going to derive with this in mind, and using this notation, we're going to derive the algorithm. The parallel sparse matrix vector multiplication for a processor PS is as follows. We'll start with the central operation, which is the local sparse matrix vector multiplication. And what we'll do here is, for every row I that's locally non-empty, we first initialize the local contribution, and then for all the j that are local, we update this local contribution by adding the product Aij times Vj. This is the central operation. But this Vj that we have here may be on a different processor. So we need to get it in superstep 0. For all the j that I need, and that's what we have the index set, the column index set JS for, we need to get Vj from its owner. That's another processor. And the owner is given by the mapping phi v. We can get this by sending a request to that processor to get it. Or if we have the address already, then we can get it directly from that processor. But in any case, the fact that I need it is known at the receiving processor. I need it, so I need to get it. So this is not a put, but here we have a get. Then, once I've done the local vector, sparse matrix vector multiplication, I can use these results. And what do I have to do? I have to send them to the owner. So that's superstep 2 for I in the index set. So I'm sending put the result UIS in the processor that is responsible for computing the results. It's the owner of row I, of component I of the vector u. And then the final superstep will be to add all these up. So what I do is, if I am responsible. So for all the components I for which I am responsible, so phi u of I equals S, then what I do is I initialize to 0 for all the elements that I received for the t between 0 and p. So this says who is the sender, the target processor. So for all the t that contributes something, we add ui t to ui. Okay, so this last step, we add contributions uit only if they are non-zero, which means only if they have been sent. So we don't perform this test, but anything that we receive, we just add to the appropriate UI. That's how it works in practice. Okay, so we've seen the notation of the algorithm. The notation we're familiar with by now, but we can also visualize the algorithm, where the arrows in this picture, they denote communication. For example, in column 0, you see that we communicate the element 2 from the blue processor to the red processor because it needs it, for example, to multiply by 4. And this vertical arrow then means 1 data word of communication. We do not need to communicate everything. For example, column 1, you see that all the elements in the column are non-zero, but also the vector component, v1, is non-zero, is red, and because of that we don't need to communicate. At the end, we get results, partial results, contributions to the output vector ui, and that may again require communication. For example, if you look in row 0, we have the output of the blue processor. We have multiplied 3 by 1, we get a number 3, and we need to communicate that to the red processor. So that's why we see a horizontal arrow. And this arrow denotes 1 data word of communication. So this is what we need. Then in the BSP world, we always ask of algorithms, how much does it cost? We actually also in the real world ask this question a lot in many different languages. But here we ask for a sparse algorithm, sparse matrix vector multiplication, how much does it cost? And that's usually not a question that's so easy to answer for sparse algorithms, unlike dense algorithms. The sparsity has a big influence on the cost. And we need to make some assumptions to facilitate analysis. And our assumptions will be then load balance assumptions. We assume that the non-zeros are spread evenly over the processor. So if we have nz non-zeros, it's nz divided by p non-zeros locally. And here in the formulation, we assume that we have c non-zeros per row. So then it becomes c times n divided by p. Also, we assume that the vector components are spread well, so every processor has n over p processors. And then we can analyze the 4 steps of our algorithm, the 4 supersteps. So superstep 0, in the worst case, you need all vector components, and except, of course, the ones that you already have stored locally, n divided by p. So what you need to receive in the worst case is n minus n over p. What you need to send is you have locally n over p elements, vector components, and you have to send them, in the worst case, to all other processors, so p minus 1. And that gives actually the same expression, the sending in the worst case, as the receiving in the worst case. So t0 is a little bit less than n times g plus L. Superstep 1, that's an easy one because we made an equal spreading assumption. So this is perfect. We have 2 flops per non-zero, so 2Cn divided by p plus the L for the superstep. Superstep 2 just looks like a superstep 0, so the fan-in looks like the fan-out and has the same cost. And the last superstep, superstep 3, there we add all the local contributions of the different processors. So each may contribute n over p elements, and we have p processors. So altogether we have n flops in the worst case. So adding this up gives a formula, and in this formula we see 2Cn divided by p as the main term. We see a communication term which is about 2n times g and 4 times L. And this bound is pessimistic because the communication can really be improved. The synchronization, well, 4L doesn't matter that much. It's a constant number of supersteps, small number, and the computation is well balanced, so we can't improve that. So we define the communication volume V of an algorithm as the total number of data words that are being communicated. And in this case, V depends on phi, so we write it as V with a subscript phi. And we can make an estimate, or lower bound it, by counting in every row of the matrix, row I, the number of processors, lambda I, that's present there. Because then a lower bound would be lambda I minus 1, in case the vector component ui is assigned to one of the processors that's present in the row. We only need to send it to all lambda I minus 1 others. Actually, an upper bound would be, if we don't have this pleasant situation, then you would have to send it from a processor that's not present in the row to all lambda I others. Okay, so summing this, and we also define mu j similarly for the columns, we get an expression, the sum of lambda I minus 1 plus the sum of all the mu j minus 1 gives v phi. And then if we want an upper bound on the communication, we have to add 2n, because then we just have to skip those minus 1s, and we get 2n extra. Okay, a summary of what we have seen. We distribute the matrix first, assigning non-zeros to processors, and then we represented those non-zeros in the processors. And we have a mapping phi for the matrix, phi u for the vector u, and phi v for the vector phi. We've seen we have an algorithm with 4 supersteps. We start with a fan-out, then perform a local sparse matrix vector multiplication, a fan-in, and then we add some partial sums to get the final result. We've also seen a row index set IS, a column index set JS, which represent the non-empty rows and columns of the matrix. So I have a final question to you. We look at a very specific matrix, a tridiagonal matrix, which has non-zeros on the main diagonal, one diagonal above it and one diagonal below it, and we just define all elements to be 1, but that doesn't matter really that much. And then we assume that we have a block row distribution. So phi ij is just I divided by b, where b is the block size, and that's just n over p. We assume that everything is easy, so that p divides n. We also assume that p is big enough. Let's say p is larger than or equal to 3, and that the block size is also larger than 2. Otherwise, it would be a very trivial problem. And We also assume that the vectors are in the same distribution, so a block distribution with block size b. And now the question, compute the BSP cost of our parallel sparse matrix vector algorithm and also compute the communication volume of this algorithm for this particular matrix.